Okay. So I'm going to give you guys a periodic table so you don't have to keep flipping to the beginning of your book. There is one though in the very beginning of your book. So if you like leave yours behind or something, you always have a backup. Yes? But we'll give you a nice green one so that it's easy to find. You can be like, oh, it's the green one. Yeah, cheers. 1, 2, 3, 4. I, I, I don't know. I don't see him. Why is everybody late today? You got water. Okay, so just to familiarize you with what is in your workbook, you should know that you have your periodic table. On the second page, which is also the back of the green sheet, you have an alphabetical listing of elements. This is really nice. If I say to you, go find osmium, and you're like, I don't know where osmium is because that's not a very typical element, you can look under O for osmium, and you can say, okay, osmium is atomic number 76. Then you can go back to your periodic table, and you can look under 76. You'll notice it goes up 1, 2, 3, 4, all in a row. Number 76 is right here after 75 and before 77. Yes? So those are nice to have. Another thing that's nice to have, this is on the third page, I think, is just a summary of finding atomic particles. So if you get stuck at some point, this is on page 3, I think. Let's check. Page 3. If you forget and you're like, I am expected to write a symbol for an element and I need to write some numbers around it, what are all those numbers? Well, this one tells you that if you write the potassium like this, what goes at the bottom left? The atomic number. And where do you find the atomic number on the periodic table? At the top, which also, if you forget, on your periodic table, well, look at that, it labels it for you. Yes? Yes. Yes. And if you're like, oh, well, there's numbers not only at the bottom where I have my atomic number, but there's another number at the top. What's that? Well, this sheet will tell you that it is the mass number. And what is the mass number? Oh, it even says it here. It's the neutrons plus the protons. Okay, so this is very nice here. Oh, I've forgotten how to find the number of protons. How do I find that? It's equal to the atomic number. I want to find the number of neutrons. How do I do that? Oh, it's not on the periodic table. See how that's not, there's nothing there? Number of neutrons is not on the periodic table. You take your mass number and you subtract the atomic number, which is also the number of protons. Oh, I need to find electrons. What do I do? In a neutral atom, it is the same as the number of protons, because if you have the same number of negatives and positives, then guess what? It's 0 overall. And of course, protons is the same as the atomic number. Now, what if I have an ion? Okay. Find the number of electrons in a neutral atom. If you have a negative charge, then just add extra electrons. So if it's -2, add 2 electrons. If it's +3, take away 3 electrons. All right. And if you want to find the charge of the ions, if you have more electrons, it's going to be negative. If you have less electrons, it's going to be positive. Not that you need to remember all of that right now, but by the end of this unit, you are expected to know all of that, and you have that little reference sheet if you forget. Okay? Here we have another lovely reference sheet that reminds you of all the names of things. So if you're like, oh, I can't remember my names, guess what? They're right there on page 4. Yes? Do you remember, if I go to the other one, let's go to the one that's not labeled. Do you remember the name of group 1? What's that group called? Yeah, those are your alkali metals. How about group 2? The alkaline earth metals. So this one only has 1 word in front of metals, group 1. This one has 2 words in front of metals, group 2. Okay? Now, how about this middle bit in here? Do you remember what those are called? Transition metals. And then we have 3 groups that don't have names. Okay, we have group 13, 14, and 15. They don't have names. If you want to, you could call them the boron group, the carbon group, the nitrogen group, or you can just call them group 13, 14, 15. You remember group 17. 17 is the halogens or halogens. Doesn't matter how you pronounce it, both are correct. And how about the last group? Noble gases, okay? So a lot of this unit is review of grades 8, 9, 10, okay? Well, we are going to review through it, and Tyler's got your back, okay? There's a whole, the first section is all Tyler teaching you stuff, if you've forgotten, okay? Now, I don't know if you learned this in your junior grades, but these also have names down here. This first row of the section below the table, what's the name of that first element? Lanthanum, yes? Lanthanum. Do you know what those are called? They're called the lanthanides. This one down here is called actinium. Actinium, can you guess what this row is called? The actinides. So we have the lanthanides start with lanthanum, And the actinides start with actinium. And don't worry, you'll get practice with this along the way. I'm just, you know, kind of going through the just the reference material so that you know it's here, and a very, very small reminder of things. Now we do have the metalloids. Do you guys remember the metalloids? Does that sound familiar? Where do we find metals on the periodic table? Metals are, do you remember the staircase? Metals are which direction from the staircase, left or right? Left. So all our metals are over here. We have our alkali metals, alkaline earth metals, transition metals, and other metals. They don't have a name, okay? There's other metals. So metals, 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 and in fact, these guys down here, also metals. So most of your periodic table is made of metals. What do we have up on the top right? This side of the staircase. These were all our metals. These are our nonmetals. So the halogens are nonmetals. The noble gases are nonmetals. And then we have a very small section, which is the other nonmetals. Okay. And then we have these sort of darker gray ones. Those are our metalloids. They're the ones that touch the staircase. Okay, so the ones that are touching the staircase, except for this one, which is a metal. Does anyone know what this one is here? That's aluminum. And if I were to say to you, is aluminum a metalloid or a metal, what would you say? It's a metal, because you just know that, right? We worked with aluminum foil, right? And that's definitely a metal. It's, you know, shiny, it's metallic, you know, all those good things. Okay, that's enough of that. Oh, patterns in the periodic table. This is going to come in handy later, okay, because you can see there's all the Bohr models for all of the first 20 elements. You can refer to that at any time if you need to kind of go, oh, what should this look like? All right, what else do we have? So many references. Oh, how to draw Lewis structures, that'll be at the end. So we'll skip that. Did you watch the video? The 7-minute video? What's that? I didn't post it. Oh, I'm so sorry. It should have been on Teams. I had like a little, I don't know. I had like a little mental breakdown yesterday. I was just like so tired, like sleepy tired, like after school. I cleaned up and I just went home and then I fell asleep. So I'm sorry. Let's see if we can do this without the video, shall we? Because I believe you can. I think you know most of this stuff already. Here we're zooming in billions and zillions and zillions of times. And we have some table salt. What structure is that? It's an ionic crystal lattice, yes. And is it a pure substance or is it a mixture? It is a pure substance. Okay. It's an ionic crystal lattice. It's a pure substance. What type of pure substance is it? There's two types of pure substances. What are they? Elements and the other things. Pure substances See how we're reviewing here? Can be elements or compounds. Okay, so pure substances, elements, or compounds. So we have a pure substance down here. Is that an element? No, it is a compound. What kind of a compound is it? It is ionic. We have a liquid, we have some water. What is this made of? It's not an ionic crystal lattice this time. What is it? We have molecules. It is a molecular compound. Are we okay with CMPD for compound? Okay. And that's also known as what? A molecular compound is also known as a covalent compound. Okay. Is this a pure substance or a mixture? It's another pure substance, pure. And our gas over on the side, oh, is it a compound or is it an element? This one over here is an element. Yeah. And what's it made of? 2 oxygens, so it is a molecule. It is a that, this a that? Okay. So everything is made of atoms. Atoms are the building blocks. For all matter. Atoms are super tiny. And I don't remember how many atoms lined up it would take to be as thick as the piece of paper. I just don't remember. A lot. Maybe we should watch Tyler for this part. 1 million? Let's zoom even more. Atoms are the building blocks. For all stuff, but an atom has even smaller building blocks. That make it up. The building blocks of the atom are what's zooming around the outside? Electrons. What do we call that in the center? That is our nucleus. And what do we have in the nucleus? Neutrons and protons. I'm going to call these protons just because. And neutrons. What charge are our electrons? Negative. What charge are the protons? Positive. And what charge are the neutrons? Neutral. Anything new here or anything we've forgotten? Are we mostly remembering this? Good. Okay. Oh, okay, so we're just labeling them here. The electrons are negative, the protons are positive, the neutrons are neutral. I think I need my answer key for this. I don't know the numbers. Oh, it's not even in here. Is it? Oh, yeah, it is. No. You can tell me? Oh, excellent. What is it? Ah, 1 proton. The mass of 1 proton or neutron is 1.67 times 10 to the negative 24 grams. That's a really small number, yes? So it is much less than 1. I mean, if you look, we've got so many zeros, yes? Wouldn't it be nice to have another unit to measure that in rather than 0.0000000000000? So we give it the name AMU, which stands for atomic mass unit. Oh, 1 AMU? Oh. Maybe I should just wait. Should we just watch the video at this point? Yes, okay. All right. I'm so sorry, I forgot. Tyler DeWitt, basic atomic structure, okay. I know you guys rely on it. I just, like I said, I just kind of fell apart a little bit yesterday. Okay, here we go. Tyler? Oh. Do you know what's really interesting? There's a video of him along with Paul Anderson, who does Bozeman science, who you'll see a lot if you do biology. And then there's another guy who does calculus, whose name I can't remember because I don't ever do calculus. But the three of them are together at a conference, and they're just talking about their first, like their university experience. And Tyler's talking about like his first test, his chemistry test at university that he got back. And they handed all the tests back, and the professor puts the highest mark and the lowest mark on the board for everyone to see. And Tyler looks at his paper, and guess what? Lowest mark in the class. Lowest mark in the class. So the moral of that story is, if you're interested in it, you try harder and you keep working at it, okay? But you're not gonna get there without a lot of sweat and effort, yeah? Anyway.
Atoms are the building blocks that make up everything.
Okay, so let's skip ahead to where we've got the AMU.
These atoms here, and in the center of the atom is something called charge. One electron and actually touch the protons. Look at what a tiny number this is, right? There's a decimal place all the way over here. This is a number that it's best to represent in scientific notation instead. But however you write this, it's a really tiny, unwieldy number. So scientists came up with another way to measure the mass of a proton or neutron, and that's using a unit called the AMU, the atomic mass unit. And they said, okay, one proton or one neutron weighs about 1 AMU. That's a lot easier to use than this measurement here. So a proton or a neutron weighs about 1 AMU. An electron, on the other hand, is much, much, much smaller than a proton or a neutron. It weighs only 0.000549 AMU. So a tiny...
Okay, so you can fill that in. Mass of one electron. One electron is 0.000549 AMU. Are you expected to remember that number? No. All you need to know is that it is much, 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 much smaller than the mass of what? Proton or neutron. So when we are finding the mass of the atom, we basically just ignore the electrons. We just add up the protons and neutrons and ignore the electrons completely. Oh, no, there we go.
Tiny fraction of how much a proton or a neutron weighs. For this
Well,
reason,
go ahead.
when we're talking about the mass of atoms, which we'll talk about later on, we usually add up the protons and neutrons to find out how many AMUs the atom weighs. And then we usually don't even worry about the electrons at all because they're so tiny. They don't really have much of an influence on how much an atom weighs. It's like when you get on a scale to weigh yourself, you don't worry about the ring you're wearing or whether you're wearing a necklace or something, because those things are just so tiny, they weigh so little compared to how much you weigh, that it doesn't really influence your weight. So, protons and neutrons, 1 AMU, and electrons, a tiny fraction of them. Now, I said that the atom, the way it's drawn here, isn't a perfect representation of what atoms would actually look like. We'll talk more about that later, but there are two things that I want to bring up for right now. The first is the electrons and how they move. This drawing might make you think that the electrons are spinning around in nice circles on the outside of the atom.
Is that what electrons really do? No, do you guys know what they do? They buzz around like hyperactive flies. Yes, they do. But more correctly, they form a probability function, which we'll look at later and then go, we're not going to understand this.
That's actually not what happens. They're buzzing around much more randomly, kind of like hyperactive flies all over the place. We'll talk more about that later. The second thing has to do with the size of the nucleus and how far the electrons are from it. If this were a real atom blown up many, many times, and the nucleus were the size of a grape, the electrons out here would be almost a mile away. So have this grape size.
So if the nucleus were the size of a grape, the electrons would make a cloud that reached out to about how far away? A mile. A grape, a mile. A grape, a mile. Big difference, right? Nucleus, very, very tiny. Electron cloud, really, really big, except for still really, really tiny because it is an atom, right? Most of an atom is actually, do you know what? Empty space. It's not air because air implies that there are atoms floating around. It's just nothing. It's empty space.
Size nucleus, and a mile away would be the electrons spinning on the outside. So that means that most of an atom is actually empty space. Anyway, now that we've talked about what an atom looks like and the particles that make it up, we can go and discuss some of the characteristics that we can use to describe atoms. These are things like...
Okay, we're going to talk about that later. We're now going to look at what are isotopes. Do you remember what an isotope is? Tell your partner if you can remember what an isotope is. It's like an element, but with a weird number.
What are isotopes? Isotope is a word that gets thrown around in chemistry a lot. So, like, what are they? Really quickly, isotopes are different versions of an element, or different versions of a certain...
So they're different versions of what? An element. So you got all the same element, just different types of that same element.
Kind of atom. This can be a tricky concept, though, and a lot of people get confused by isotopes. So I want to describe them by starting out with an analogy to cars, okay? I want to talk to you about the made-up car called the Lamona, the epitome of luxury, and it's known for its very distinctive style. As you'll see, the Lamona looks like a lemon. Now, the Lamona comes in 3 different models. There's the Lamona G, the Lamona GX, and the Lamona GXL. They're all different colors, as you can see. But each of these models also has unique features. One has a radio and leather seats. The GX here has chrome wheels and a CD player.
You can tell this is dated because there's a CD player in the car. I still have CD player in my car.
Blue. The red GXL has massaging seats, platinum spinner wheels, and everything. But here's the point. They are all Lamonas. They're all Lamonas because they all have this distinctive style. They look like a lemon, and that's what makes a car a Lamona.
Now I want you to notice with the name, how does the name distinguish which model you have? You write Lamona, and then what do you write? Dash G. You write Lamona, and then you write dash GX, and you write Lamona, and you write dash GXL. This is an analogy to what you will be doing for your isotopes. Kind of, yeah.
Okay? So it doesn't matter what color it is, and it doesn't matter the various options that you get in these models, the GX or the GXL. What matters is that they all have this particular shape. That's what makes a Lamona a Lamona. So we have these 3 different models.
And if you don't know why it's called a Lamona, a car that doesn't work very well is often called a lemon. Okay, so that's where the Lamona comes from.
I want to use this analogy now to talk about the same thing but with animals. I want to now introduce you to 3 models of carbon, just the way there are 3 models of Lamona. Okay? Here are the drawings of each one of them, and what we're particularly concerned about is the nucleus. I'm using these red dots to symbolize protons, and I'm using the blue dots to symbolize neutrons. The swirly circles are supposed to represent electrons that are buzzing around the nucleus, but we don't really want to worry about that too much. Anyway, these 3 models of carbon are carbon-12, carbon-13, and carbon-14. Let's look at the options in it.
You guys remember what it means to say carbon-12, carbon-13, and carbon-14? Yeah, those are the number of protons and neutrons together, because each of those protons and neutrons weighs how much? 1 AMU, 1 atomic mass unit. So if you add up 6 protons and 6 neutrons, how many AMU do you have? 12. And what if you added another neutron? So you had 7 neutrons and 6 protons. What would you have? 13. Okay.
Like we did with the Lamona, let's look at how each one of these different types of carbon differs. Okay? So if we count the number of protons in carbon-12, we'll see that it has 6 protons. And if I count all the blue spots here, I have 6 neutrons. Okay? Carbon-13, 1, 2, 3, 4, 5, 6. Red spots, 6 protons. In this one, I have 7 neutrons. And in carbon-14 down here, I have 6 protons, and I have 8 neutrons. So what do we have in common here? All the different models of the Lamona, even though there are things that they...
What do they all have in common? The amount of protons. What would happen if I changed the number of protons? It becomes a different element. So 6 protons defines an element as being carbon. If I changed it to 7, instead of having carbon, who would you have? You would have nitrogen, which is atomic number 7. Okay.
Different about all have the same distinctive lemon-like shape. So for carbon, what they all have in common is they have 6 protons. 6 protons in the nucleus. And that's what makes a carbon atom a carbon atom. Okay? So it turns out that it doesn't matter how many neutrons it has. 6 neutrons, 7 neutrons, 8 neutrons, no big deal. It's just like painting the Lamona different colors or adding a radio or a CD player. The neutrons, it doesn't matter. It doesn't change the fact that each one of these are carbon. That's because carbon is defined by the fact that it has 6 protons in its nucleus. If you look it up in the periodic table, you'll see something that looks like this, and the number up here is the atomic number, 6, which means that if an atom has 6 protons, it's a carbon. Okay? So that's what these all are. They are all isotopes of carbon. They're different versions of carbon, or different models of carbon, the same number of protons and different number of neutrons. So look at how I wrote this. I've got carbon 12, carbon 13, carbon 14 up here. I want to take a minute and talk about the numbers.
Okay, so when you are writing the name of an isotope, what do you write? You write the name of the element and then what? A dash, and then what? Ooh. What's this number here? That's AMU, and it's going to be the number of what plus what? Protons plus neutrons, and that has a specific name. Does anyone remember what that's called? It's called the mass number, which is different than the atomic mass that you have on your periodic table, and we'll talk a little bit about that later. Okay, I'm like showing that. Okay, so this is the mass number. What's the mass number equal to? That's sad. My grade 9s could answer this. What is the mass number equal to? Protons plus neutrons. What's the mass number equal to? Protons plus neutrons. What if I told you you have carbon 14 and I hid that number there? Could you figure out that the neutrons was 8? How would you do it? 14 minus 6 gives you 8. So as long as I give you the mass number, you can figure out the number of neutrons.
So the number of protons in the nucleus, we call that the atomic number. You may already know that. And then carbon 12, this 12 that I've written here, refers to a different number, and we call that the mass number. The mass number, as you'll see, is the number of protons plus the number of neutrons. So this is carbon 12. 6 plus 7 protons and neutrons, 13 here. 6 plus 8 is carbon 14. So that's how we distinguish between these different isotopes, different types of carbon. There's another way that we sometimes indicate these different isotopes of an atom instead of doing 12 and 13 and 14, and that's by using something called isotope notation. Let me show you how we do that. The way we write carbon 12 or 13 or 14 isotope notation is we start out with a chemical symbol. If you don't already know that, you can find it on the periodic table. So here it is. It's a big uppercase C. So I start with my C for carbon. And then on the lower corner here, I write the atomic number. So that's going to be 6. And then up top, I write the mass number, which is 12. So this is carbon 12 written in isotope notation. Carbon 13 is going to be 6 again, because all carbon has 6 protons in its nucleus. Then the 13 up here. And finally, carbon 14, written in isotope notation, is C614.
Okay, so you are expected to know how to write both the name with the dash and the, what's that number called? Mass number. What's the mass number equal to? What's the mass number equal to? Protons plus neutrons. Okay, you are also expected to be able to write the symbol, which is also known as isotope notation, where instead of writing the whole word carbon, you write the symbol. And your numbers always go on which side? The left-hand side. Where does the bigger number go? It goes on the top. Where does the smaller number go? On the bottom. If you have trouble remembering that, it's just like the floors of a building. The lower floors have smaller numbers, the higher floors have higher numbers, yes? I think the reason that they chose to write it this way is because when you subtract, usually you stack numbers one on top of the other. So if you wanted to find the number of neutrons, you would go 12 minus 6, and you would get 6. You would go 13 minus 6 gives you 7 neutrons. 14 minus 6 protons gives you 8 neutrons. And I think that's why they do them in like the bigger number on the top and the smaller number on the bottom, is because visually it makes it easier for subtracting. So
that's how we can write all these isotopes of carbon in isotope notation. Then, of course, you can also write it as just the element name with a dash and then a number. So carbon isn't the only type of element that has multiple isotopes. In fact, just like cars, almost every form of element comes in multiple isotopes. Here are the calcium isotopes, for example. If you look up on the periodic table, you'll see that calcium has an atomic number 20, which means that any atom that has 20 protons in its nucleus is calcium. But just like with carbon, you can vary the number of neutrons that are in the nucleus. You get all these different isotopes, but you still have calcium.
There are not unlimited isotopes. Calcium happens to have 6 isotopes that occur in nature. Okay, I'll just give you a minute to fill in the little bits and bobs on there. I'm not quite sure why I had you fill that in, but I did. But at the top of the periodic table, and this is a little bit irritating, because at the top of the periodic table, square, that's our atomic number at the top. But when we write the isotope notation, we don't write that 20 at the top, we write it at the bottom left. Okay, because that's our number of protons. Just so you don't get confused with that. Okay.
Calcium, we've got 40, 42, 43, 44, 46, 48. All of them have 20 protons in the nucleus, but they have varying numbers of neutrons. Just like we did with carbon, we can write all of these calcium isotopes in isotope notation, where we have the mass number here at the top and the atomic number down at the bottom. You'll see they all have the same atomic number of 20, but different mass numbers, the sum of protons and neutrons. The same is true for iron, just to give you another example. Iron has 26 protons in its nucleus, an atomic number of 26. And there are 4 known isotopes of iron, all of which have 26 protons in the nucleus, but they all have varying numbers of neutrons. You add these together to get the mass number, and then you can write it in isotope notation with the mass number up here and the atomic number down here. So just to review what we've talked about, atoms come in different versions known as isotopes. These are like the different versions of a car or something. The number of neutrons change, but just as long as you have the same number of protons, you still have the same type of atom, same type of element. You can take an atom and write it in isotope notation, where you put the atomic number on the bottom and the mass number up here. So that's what I see.
Okay. Now let's go look at our periodic table for a moment. All right. So now on our periodic table, you can see that we have the atomic number. Is there a mass number on the periodic table? There's no mass number. And the reason for that is because the mass number is different for each isotope. So you would have to have a list of all the little ones, and if you had to fit 6 of them on your periodic table, that would be really, really awkward, yes? So instead of having a mass number, we have a different number which is similar but not the same. What is that? That is our atomic mass. And we're going to let Tyler talk about why we can have, even though a proton and a neutron weigh exactly 1, how is it that we can have a 0.1, or ooh, look at chlorine, 35.5, 20.2, right? Those do not look like whole numbers of protons and neutrons. And you might think to yourself, I wonder why that is. See if you can tell your partner while I load up the next video. Yes, of course. Why are these different? I think they're the same. Yeah.
Let's talk about the difference between mass number and atomic mass. These things sound very similar, but they're actually very different. Just so you know, atomic mass can go by other names. Sometimes it's called average atomic mass, or relative atomic mass, or even atomic weight. Maybe your teacher calls it one of these. For our purposes, in this video, we're just going to call it atomic mass. So, we're talking about the difference between these two things. Let's start by talking about mass number. So up here, I've got two atoms. They've got protons and neutrons in their nucleus, and I'm particularly concerned with the number of protons and neutrons that there are. So this atom over here has 5 protons. The protons are these red circles. We can count them up. 5 protons, and the neutrons are these blue circles. We can count them up. We've got 5 of those. This atom over here also has 5 protons, but it's got 6 neutrons.
So you guys should be able to, at this point, calculate the mass number for the atom on the left and the atom on the right. So what is the mass number for the atom on the left? At least 10. Yes, kind of. It is exactly 10, okay? How about the atom on the right? 11. And I'd like you to notice, beside the word mass number in your book, what letter is in brackets? A. I don't know why they call it A, because that would sound like atomic mass, but the letter A represents the mass number. And the letter Z represents the atomic number. So chemists, what can I say? They came up with silly things at some point, and then they just stuck with them. Okay?
So,
oh, which atom is this? Which element do we have here? Boron. Boron is atomic number 5. We have 5 protons, so we know it's atomic number 5.
mass number is the number of protons plus the number of neutrons. So this atom here has a mass number of 10, 5 plus 5. And this atom over here has a mass number of 11, 5 plus 6. Mass number tells us how many protons and neutrons are in the nucleus of an atom. But it's also important because it gives us an idea of how much the atom weighs.
How much does the atom on the left weigh? 10 AMU. And the atom on the right? 11 AMU.
You might remember, we've said before that 1 proton or 1 neutron weighs about 1 AMU, 1 atomic mass unit. So, if you have a mass number of 10, 5 protons and 5 neutrons, your atom is going to weigh about 10 AMU. If you have a mass number of 11, that tells you that the atom here weighs about 11 AMU. These atoms both have electrons, but electrons are so tiny, and they have such a small amount of mass that we don't even worry about the mass of electrons when we're weighing up stuff to determine how much the larger atom will weigh. So,
we're going to take a pause for just a second and go to here, 3.1c. Because Tyler doesn't actually like write this down at any point. So the mass number is the mass of a specific isotope. Okay, so you pick one atom out of wherever and you say, this one has 5 protons and 5 neutrons, and that gives you your mass number, okay, for that specific isotope. So it's the number of protons plus the number of neutrons. These are always going to be whole numbers. How could you have a fraction of a proton? It stops being a proton. I think protons are made out of weird little things called, I don't know, quarks, and there's leptons, and there's muons, and I don't know any of those because nobody thought it was important to teach those things when I was in school. And I'm okay with that. I don't need to understand it. You don't. No, you don't. You don't need to know about leptons or muons or quarks or any of those things. You just need to know that you cannot have fractions of protons and neutrons. So the mass number, since it is the number of protons and neutrons, there's no decimals. No decimals. Whole numbers only. And you also should know that the mass number, you cannot find it on the periodic table. You might want to find it on the periodic table, but it is not there. Okay? And it is the one that we write up at the top left or after the dash. That's our mass number. Not the atomic mass. The atomic mass, on the other hand, is the average. Okay, that's the key thing, is that it's the average of all the isotopes. Okay, and that's why you can have fractions, right? Because when you're taking an average, you'll end up with, like, if you have 50, 50, 9, and 10, your average would be 9.5. Okay. These do have decimals, and these are the ones that are on the periodic table. And we do not write like this. We don't say chlorine 35.5. That would be a big no. Okay? We do not write chlorine 35.5. Again, that would be a no. That is a crazy chlorine with like a little half proton or something. I don't even know. Half a neutron. All right, back to Tyler.
(10 AMU, 11 AMU. So that's mass number. Protons plus neutrons, and it gives you an idea of how much the atom weighs in AMU. Now, let's talk about atomic mass. You might notice that both of these atoms have the same number of protons in their nucleus. 5 protons here and 5 protons here. This means that they're the same element, right? Because the number of protons an atom has determines what kind of an element it is. So, we can look on the periodic table to find out what element these atoms are, and it turns out that they're boron, because boron up here has an atomic number of 5. 5 protons and your boron. So, both of these atoms are different versions of boron. They're different isotopes. An isotope is a word that just means a different version of an atom that has the same number of protons, but a different number of neutrons. We can give distinct names to these two isotopes or versions of boron.
What would we call the boron on the left? Boron dash 10, and the one on the right? Boron 11. Boron dash 11.
This atom over here is an example of boron 10, because it has a mass number of 10, 5 plus 5. And this atom here is an isotope of boron called boron 11. 5 plus 6 has a mass number of 11. So, there are billions and trillions and gazillions of boron atoms in the world. If we could pick one up at random, it could be either one of these two types. Okay, it could be a boron 10 atom with 5 protons and 5 neutrons, or it might be a boron 11 atom with 5 protons and 6 neutrons. So boron comes in these two versions. Now the thing is, there is not an equal number of boron 10 atoms and boron 11 atoms. In fact, if we pulled 50 boron atoms at random and represented them here, we see that the majority of the boron atoms are boron 11, which I'm indicating with little orange circles here. Okay, most of them are boron 11, and only a small minority of them are boron 10 atoms. We can look at this on a pie chart just to get this point home, and you can see that the vast majority of them are boron 11, with a smaller amount that's boron 10. If you crank through the math here, you'll find out that about 20% of the boron atoms in the world are boron 10, whereas 80% of them are boron 11. This leads us to the idea of atomic mass. Now, atomic mass asks, what is the average mass of a boron atom? All right? We've got these two types of boron atoms. We've got boron 10 that weighs 10 AMU. That's what its mass is. And we've got boron 11, which weighs 11 AMU. That's what its mass is. But here's the thing. There's only 20% of this guy and 80% of this guy. So now we're asking, got these two types of boron, what is the average mass of a boron atom? Now, you might think average and say that's pretty easy. I know how to take an average. This guy weighs 10, this guy weighs 11. So why don't I just add the two of them up, 10 plus 11, and divide by 2? And then I'll get 10.5, right? That's how I take an average.
You like that? No. Why not? It's not representing the proportion of the atoms, right? Because we don't have a 50-50 mix.
Okay? No, it's wrong. That is one way you can take an average, but it won't work here. And the reason why is because this type of thing, added up and divided by 2, assumes that we have the same amount of both of these. If we had 50% boron 10 and 50% boron 11, then we could just add them up and divide by 2. But we can't do that because we have different amounts of these two types of atoms. Okay? And we have to come up with a mathematical equation that's more complex than this to take into account the different amounts that we have of these two atoms. Here's how we do it. We take the fact that there are 20% boron 10 atoms and that they weigh 10 AMU each, so 20% times 10 AMU. And then we add that to 80%, which is over here, times 11 AMU. And when we do that math, we have to convert the percentages into decimals. But when we crank through this, we end up with 10.8 AMU. And this tells us what the average weight of a boron atom is, taking into mind that only 20% of the boron atoms out there are boron 10, and 80% of the boron atoms out there are boron 11. Now check this out. The number that we get here, 10.8 AMU, is what's the bottom of this element name on the periodic table. So that's what this number is. It's the atomic mass that tells you what the average weight of one of these boron atoms is. Now we said we had these two different types that weigh 10 AMU or 11 AMU. Look at the average. The average is 10.8, which is much closer to 11 than it is to 10. And that makes sense, because since we have so many more of these and they weigh more, the average for these two types should end up closer to this, just because we have so many more. So that's how we determine what atomic mass is. Just to review these two things.
So are we good with that? We want to listen to his review? Okay.
Mass number is a number of protons and neutrons in a particular atom
or in a particular isotope. And from the atomic number, you can figure out how much the atom weighs in AMU. But now atomic mass looks at all the different types of isotopes for a particular element, in this case boron 10 and boron 11. It takes into account the amount of each that you have, also known as the abundance, how many of them there are, and then you do this math, taking into account the abundance to find the average mass of all of the different types of boron. So that is the difference between mass number and atomic mass. If you want to learn more about how to calculate atomic mass, I've got videos on that.
So that's been our review of atoms. Now, we haven't dealt with ions yet. We'll deal with those later. But in a neutral atom of nitrogen, how many protons are there? 7. How many electrons are there? 7, because it's neutral. Okay? So at this point, you could work on, until the halfway bell, 14, 17, 20, 26 to 30. All the stuff that deals with neutral atoms. Yes. Anyone else need a workbook? Who wasn't here? Good. I'll put those up bigger. 14, 17, 20, and 26 to 30. Yeah. Well, it's the one place where people, even though they've done it for years, so I'm just going to let you guys know, I'm going to put all the extra periodic tables in this little thing over here. I think it's the only green thing. If you ever lost your periodic table, there are extras right here, the green one. Oh, it's so neat and tiny, and everything's around. I photocopied it last year. And it's been sitting in this folder in my drawer ever since. Please call me over if you have questions. I'm just marking something, but you're more important than that, so. Hi. Yep. Either is fine. It's break time. And technically we get a 5-minute break, but if you're like, if you take 10 minutes, I'll be okay with that because it seems not really nice to like, yeah. So be back in 10 minutes, okay? Okay, my friends, how far did you make it through here? Not far? You're on 20? How far did you guys make it? 27? 29? Do you want another 15 minutes to work on this? Okay. We'll give you another 15, so till 2:15. There you go. Yes. Do you guys want to do a POGL for the rest of class? A POGL, it's the group thing. You can pick your groups, okay? But I will help you find a group if you do not have a group, okay? So this is on page 57, okay? Page 57. Oh, no, 57 to whatever the end of it is. 57 to 61. Yes. Hang on one second. To 61. So, my friends, I see one group. I see one group for doing the POGL. Okay, we have two groups. You guys are a group of three? Can I have a couple people join me? Yes? Excellent. Can you two come and join you three up here? Okay. Do I need to write the result every below this? Right in the thumbnail. Yeah, you're right. 12, 12, 12, 12, 12, 12, 12. Yes. Yep. Yep. Yeah, go for it. Process-oriented guided inquiry learning.